You are welcome to study session 11. The last time it was study session 10, and we considered acids, bases, and salt. Today we want to consider study session 11, and the topic is nuclear chemistry. At the end of this study session, you are expected to have been able to do the following. 1. You list and differentiate between types of rays from radioactive materials. Then the second thing you are expected to have known is to explain the measurement of radioactivity. And the third thing is to define radioactive isotopes, isobars, and isotope. And lastly, you are expected to know the importance of an application of radioactivity generally. Introduction. Nuclear chemistry is the subfield of chemistry dealing with radioactivity, nuclear processes, and nuclear properties. It includes the study of chemical effects resulting from absorption of radiation within living animals, plants, and other materials. Radiation is harmful to living things. The extent of the harm don't depend on the amount and type of radiation. Radiation chemistry controls much of radiation biology, as radiation has an effect on living things at the molecular scale. That is, the radiation alters the biological macromolecules within an organism. The alteration of the biomolecule then changes the chemistry which occurs within the organisms. Nuclear chemistry is the subfield of chemistry dealing with the rays from radioactive materials. There are 3 different types of rays. We have the alpha particles, the beta particles, and the gamma particles. A careful look at the properties of these rays shows that alpha rays has a penetrating power that is smaller with greater momentum. Beta rays has more penetrating power than the alpha particles. And the last one, gamma rays, have an extremely high penetrating power. Other properties are shown: the nature, the velocity, and the ionization of air. But majorly, the penetrating power is of utmost importance to us. Measurement of radioactivity. There are 3 different ways of measuring radioactivity. The first one is using the Gamola counter. The second one is using the Wilson cloud chamber, and using a proportional counter. Measuring rate of atomic disintegration. If you want to measure the rate, we need to know the half-life. Half-life is the time it takes for an original amount of substance to decay or degrade to half its original mass. That is the half-life. And radioactive disintegration follows a first-order rate equation as shown. If you have an equation A going to B, reactant is the A, B is the product. So the rate of disintegration will now be dN over dt equals to lambda multiplied by n. That's equation 1, where n stands for number of atoms of A present at any given time, and lambda is called the radioactive decay. If equation 1 is integrated, we discover that we have ln n equals to minus lambda t, as shown as equation 2. And turning that equation 2 to the exponential form, we have n equals to n naught exponential minus lambda t. Equation 2 and 3 can now be used to calculate the half-life of a radioactive element. Half-life calculation. Suppose after time t, half of the atoms of radioactive substance are disintegrated, meaning that n becomes n naught over 2. Here, n naught is the initial amount. N is the amount that has decayed after a particular time. So when half of the original amount has disintegrated, what you are talking about is the half-life. That now resulted in equation 4. 1 over 2 equals to exponential minus lambda to 1 over 2. And the careful evaluation is as shown in that equation 5. T half equals to 0.693 divided by lambda. This equation is very important because I'm going to make use of this equation in calculating either the half-life or the radioactive decay constant of various elements. A good example is this: half-life of radon with atomic mass 226 is 1,600 years. We have to show that 1 gram of radon disintegrates when it will give 3.66 times 10 to the power 10 disintegration per second. This question is telling us the answer already. But how do we get to the answer? That is the question. So let's see how we go about it. Going by equation 5, lambda equals to 0.693 over T half. We have been given the half-life. The half-life from the question is 1,600 years. We have to convert years to seconds. One, we convert years to days, then days to hours, hours to minutes, and minutes to seconds. Substituting that will give us 0.69 divided by 1,600 and 365, that is in days, times 24, that is in hours, times 60, that is in minutes, then another 60, that is in seconds, because our time must be in seconds. So eventually we have 1.3736 exponent minus 11 per second. Going by equation 1 that we learned a while ago, minus dn over dt equals to lambda n. The decay constant that we have got, we multiply that by Avogadro's constant and we divide by the atomic mass. So when that is done, we have 1.3736 times 10 to the power minus 11 per second multiplied by 6.02 times 10 to the power minus 33 divided by 226, and that now gives us 3.66 times 10 to the power 10. That is disintegration per seconds per gram. Like I said earlier, the value we obtain here is the same as what is given in the question. Is that we have been able to prove and show that that disintegration follows a first order going by the equation for calculating the half-life. Radioactive isotopes, isobars, and isotopes. Isotopes are atoms of the same element. They have the same mass number but different atomic number or number of neutrons. A good example is uranium decay series. Uranium, we have 238 as the mass number. 92 is the atomic number. When this one undergoes an alpha disintegration, there will be a loss of 4 from the mass number. Subtracting 4 from 238, that gives us 34. And a loss of 2 from the atomic number, that gives us 90. When it undergoes a beta decay, it reduces to 234, then 91. Another beta decay increases the atomic number by 1, and eventually we have 92. The mass number still remains the same. So isotopes are compounds or atoms which have the same mass number but different number of atoms or different number of neutrons. Isobar is when a reactive nucleus releases a beta particle, just like the example as shown here, especially from thorium to palladium. From thorium to palladium, a beta particle is lost, meaning that the mass number remains the same, but the atomic number is increased by 1. 234 was the mass number in thorium. When we go to palladium, it was 234. But going by the atomic number, there will be an increase in atomic number. So from 90 to 91. So when we have such a thing, we call such a thing an isobar. When a reactive nucleus loses a beta particle, the atomic number rises by 1 and the mass number remains the same. The last one is isotopes. These are nuclides having the same number of neutrons but different number of protons. A good example is as shown. Silicon is having atomic number of 14, the mass number is 30. If you subtract 14 from 30, you have 16. That's the same number, that's a number of neutrons. Phosphorus, on the other hand, also we have 15 as the atomic number, 31 as the mass number. Subtraction gives 16, and likewise sulfur. Atomic number is 16, mass number is 32. A subtraction gives 16. So these elements, they are called isotopes because they have the same number of neutrons, but they have different number of protons. The importance of radioactivity. It has a lot of applications. Some of them are highlighted. 1. Through radioactivity, we are able to discover new fundamental particles such as neutrons, positrons, and deuterons. Darwin said that atom is the smallest indivisible particle and element. But through research and through radioactivity, we have been able to understand that atom is not the smallest. Atom can be divided into neutrons, into positrons, and into deuterons. Second application, discovery of isotopes and isobars, as we have shown earlier. Then discovery of new elements, just like from the uranium series, we have been able to get thorium and palladium. And release of atomic energy. When such disintegration occurs, there is always a release of energy to the environment. The fifth application, radioactive tracers in surgery and agriculture are other applications of radioactivity. Rock dating. You want to know the age of rock. the age of a bone. Through radioactivity, we can calculate the age. And lastly, we are able to study carbon dating. We are able to study things that has occurred in the past, and that is what the archaeologists used in their study. Thank you for listening.